Hello and welcome to day 4 of the Institute. Hopefully you're getting overwhelmed with good information, but we still have 2 more days of hopefully very good content for you. So today I'd like to introduce Ramses van Zon from the Cython group at the University of Toronto. Ramses, take it away.
All right, thank you, Scott. Okay, are you guys seeing the screen?
Yes.
All right, and you're hearing me too, obviously. Good, excellent. So this session is going to be about HPC Python programming, and we're going to look at a few things. Python is not traditionally known as a HPC, a high-performance language, and we will have to address that. And so what I'd like to try and discuss today are performance and Python, how they relate and what we can do about things. Some tools to help you find where your hotspots are, and then a few techniques to help you make your Python as performant as possible. We'll look at Numpy, we'll look at NumExpert, we'll briefly look at Numba, multiprocessing, and MPI for Pi. The thing with Python is there's a lot of packages out there that will say that they can do either parallel programming or speed things up. I only have 2 hours, and so I picked the ones that have worked for me and that I can show that work as well. So you'll see a lot of actual timings of techniques to see if they actually work out or whether they don't. So if you're doing this on your laptop, these are the Python packages you'll have to have. NumPy, SciPy, NumExpert, Matplotlib, if you want the graphics, that is. A line profiler, memory profiler, MPI for Pi, Cython, and Numba. But if you're doing this on one of the systems, then you can just copy the code and use that. And so depends on what system you're at, but we should have a reservation on Cori for this session. So I would suggest trying that one first, so that you will find the code in global, homes, R's on HPC Python. So if you did this on Cori, so I have brief instructions here. The slides were changed, and there's new slides on the website. And they will contain all 3 systems instructions. But if you're on Cori, you would log in. I would advise you to copy the code and then try and request a resource on the system. Use the reservation equals petascale. That will give you that should get you this resource faster. And we'll only use at most 8 cores. Keep it modest here. And don't forget the -c as well either. So once you have that, when you enter that, after a little while, you should get a prompt, and you can set up the environment. So I've set up an environment that has all these packages in it already, a Python environment. And to activate it, you can just do dot. Don't forget the dot. You can also write source instead of the dot. ~rzon /hpcpy /activate. And let me know if that's working or not, or let the Slack know if it's working or not, and we could fix that later. So this is what we'll need to set up, and that's how you'll get the code. Now, I'm going to be talking a little bit in general for a little while. So after this introduction, if it's still not working for you, let us know. So the problem with Python and why it doesn't work as high performance is that every line has to be reinterpreted. And so when Python hits that line again, it has to reinterpret the line even before it can start giving it off to the actual CPU instructions you mean to do with that line. It also means that because it only has a view of a single line at a time, it can't do cross-line optimizations like a compiler would. And so you're missing a lot of the niceties that a compiler can do for you in terms of optimization. Another thing that doesn't help Python much is that it's a dynamic language. A variable called x can be a string at one time, an integer another time, and a multidimensional array the next. And so every time that Python does something with a variable, with a piece of data, it has to check what type of data it is before it can even do anything. So that again adds overhead to your computation, but also means that the way that Python objects naturally are stored is kind of, okay, I don't just have my data. With every piece of data, I also have a type descriptor. And so that means that data isn't necessarily nicely laid out in memory in a way that the CPU wants to consume it. So the optimal streaming of data to the processor is sort of interrupted. So that also interferes with maximum performance. And so some of these we'll be able to alleviate, but it's good to understand that this is why Python becomes a bit slow. And so I've got two running examples to show you how bad it can be and what you can do about it. One is a diffusion equation. We've seen this in a few of the other sessions as well. It's a 2D plate. I made it square. This is the PDE that we're solving, the partial differential equation that we'll be solving on a domain x from x1 to x2 in the x direction and the same in the y direction. We'll have boundary conditions being 0 at all sides. So think of this as a hot plate that is put in some sort of heat bath, and the heat bath is at 0 degrees. But initially, it is heated. So we have some initial condition on this plate that has heated it, and then just to be precise, P here is the density or the temperature, X, Y are the spatial coordinates, T is time, and the diffusion constant is D. What would it look like if we did this? This is our initial. The left top picture is the initial state. So think of it as 4 burners. The kind of hot plate's been switched off, and then we switch on and switch it off at time 0, and put it in an ice bucket. What would happen? And this is what would happen. You'd slowly see this heat dissipate, and become a uniform distribution. So we want to compute this. We want to simulate this. And so if we do that, we will typically discretize space in all directions. Take points some spacing delta x apart. So here's a cruder discretization of this same state. And then we will place the derivative with finite differences, so with a stencil, and we'll do an explicit time stepping. So once we figured out the right-hand side of this equation, we can time step to the next time step. If you want, you can have graphics, but I'll ask you to switch it off if you want to do the actual timing. Matplotlib in Python, an old library called pgplot in C++ and Fortran, in case you're worrying how those are done. And then all of them share. So I've got 3 versions: Python, C++, and Fortran of this code. They all share the same parameter file. By very clever tricks that you should never repeat, I can put all of the parameters in the same parameter file, diff2d params.py, that can be read by C++, Fortran, and Python. And so here's the diffusion constants, the x parameters, the runtime, the grid spacing, how often you want output, and whether you want graphics. So put this to false. I think the code has it on false by default, so that's good. The thing is, it turns out that the graphics takes the majority of the time. So we can try and improve the actual solver code, and we will see no effect if you keep graphics on. So turn this off. So there are 3 files: CPP, that's a C++ file, the F90, and the .py. They all have the same code essentially, except in different languages. And so we have to compile the Fortran and the C. So there's a makefile in the directory, so that would work. That should work, and we'll compile it. I did most of my testings on Blue Waters because I made the slides before I had my Cori account. But the same will work, just the timings will be different. And I'm timing for fairness, I'm timing the compilation here, compilation speed as well. So it took about 9 seconds. And then I'm running them. So I'm running the C code, takes about a second. I'm running the Fortran code. It takes a second and 20.26. That might be in the noise. Don't take that too seriously. But the Python code takes 642 seconds. So we find that Python, with the exact same implementation, the same for loops, the same indexing, the same everything, runs natively about 500 times slower than the compiled versions. And so the way to speed that up is to translate your Python code into C++ or Fortran. But suppose you don't want to do that. The question is, what can we do? So this doesn't look too promising for Python in HPC in general. So why do we still bother with it? So we bother with it because this is the full code of the solver in Python. It fits on one slide, well, with a little bit of cutoff, right? So you can really fairly quickly implement an idea or an algorithm in Python, and it's slightly condensed so that it would fit, but it's still fairly readable to see what it's doing. And you can't really do that in Fortran and C++. And if you're worrying about not having the graphics in this same code, well, here's the graphics too. It's one line short of fitting on the slide. So this whole application, a graphical interface plus, or graphical representation plus the solver of a partial differential equation, is fairly easy to write. So that's why we do Python. Right? We like Python because it's very easy to develop in it. It's a fairly straightforward language. The fact that things are dynamic means I don't have to worry too much about declaring things ahead of time. It's fairly concise if you're a little bit disciplined, and it's very flexible. You have lots of packages, so all of the graphics, there was already a package there. It's matplotlib. So this ease of use is a big feature of Python. It's fairly easy to learn. It's easy to use. You can still read it afterwards, and it's very, very powerful. But whether you actually really get this 500 times hit in performance really depends on what you're doing. So I'm really putting the screws on Python here. This kind of tightly coupled calculation where I have a bunch of grid points that have to communicate with their neighbors, and really all they have to do is a couple of additions and a multiply. It's not much work per grid point, so it's a very tightly coupled calculation, right? And that's where Python constantly gets in the way. It has to check for every grid point what kind of type it is. That's just not very performant. But if you've got something that does more I/O, or does a lot of text comparisons, or uses some library behind the scenes, your performance hit might not be so bad. Okay. So what we have to do, though, knowing that this is 500 times slower than the serial compiled code, is we first have to try and fix that as well as we can. Right? We could try and parallelize this code, use 500 cores on Cori, and maybe if it's perfectly scaling, which it won't be, it is now as powerful as a single core on one of them. Right? You try selling that when you're asking for a resource allocation. Right? Say, okay, I need 500 times as much as the next person because I write in Python and they write in C++. They're going to say no. So we have to think of the performance and why, if we can't do anything better, even before we're doing parallel Python. So the diffusion code is a little bit tricky to get familiar with in the span of this lecture. So I've got a simpler example, which is very much related to the calculations of pi that we've seen before. We're doing an integration, an area under the curve. My favorite integral is 7/10 x cubed minus 2x squared plus 4. Because that's way more interesting than pi. And the answer is 8.175 exactly. So we know the exact answer, and we can check that. It's the area under this curve. And we're going to do the same method as we did for pi. We will sample in the x interval, we'll sample x values, compute the y coordinates, sum them, times delta x, and you've got the value. So these are the codes for C++, Fortran, and Python. In this case, it's so simple that all of them fit on one slide, and you can read your favorite one. We're going to be working with the Python, and the other ones are for comparison. And there's no parallelization in here. So let's compile them again. It took about 5 seconds to compile the Fortran and C code. And then I run them. The C code runs in 0.6 seconds. The Fortran code here is slightly faster. Don't ask me why. The Python code takes about 100 times longer. But if you want to be really fair, it took 5 seconds to compile these things. So it's 5 seconds versus 60 seconds. It's about 12 times slower. Okay, so still 12 times slower, not great. And actually, if we ran this a lot of time, we would be stuck with the 100-fold slowdown. So let's look at this one and try and figure out what we can do with that. Okay, so we want better performance, and we're gonna look at the area under the curve as our main hands-on. But how do you know where to start? Because the code is pretty small. Like, what do we have to do? Where should we focus our efforts? What is the part that really makes it slow? And so I'm going to spend some time talking about how to figure out where your code spends its time. So performance tuning tools for Python. And so when we look at performance, when we want maximum performance, we want to maximize the utility of some resource. Right? We're talking here about supercomputing, about petascale stuff. These resources are under high demand. You should use them as well as possible. So you could be maxing out CPU power. That's great. But you could also be maxing out memory. Maybe your problem needs so many cores and so many nodes because you need the memory. Maybe it's the network. Maybe it's the I/O. But something should be maximized in terms of its utilization, right? So we're going to look at computational performance, but really what I mean in this case is the time to compute something, the wall time. And so we're going to look at that first. And for the examples that we have, that's really the restriction. Memory is not an issue in terms of bottleneck, nor is I/O or network. So what we can do, and what Python comes with standard, is to be able to profile by function. So if you're a decent programmer, you know how to write functions. You know you should try and modularize your code if at all possible. And so if you have that code and it has lots of functions, you can run it through Python and you can ask Python, hey, what function took the most time? How much time is spent in each function? And that's great. There's a package called CProfile that does that for you. But what if that's a fairly big function? You'd like to know in that function, maybe it has 20 lines, which of the lines takes the longest? And so that doesn't come standard with Python. But there is a way to do that. You can profile by line, and you have to use a package called lineprof. Line profiler. Let's see how that works. So if you use CProfile, all you have to do is run your program, in this case diff2d.py, through Python by loading the module CProfile first. And then -c cumulative is nice because you get the cumulative time as a column in your output. And so what this will show for the diffusion equation is that most time is spent in the module or in main. It looks like it's telling you what line it is in, but that's not true. Those are the entry lines. So the function main starts in line 14, and that's the only function. That isn't giving us any more information than saying the most time of your program is spent in your program. So if we want to do better, we can install this package called Line Profiler in the environment that you have hopefully activated. It's already installed, and it can do line by line profiling, but we have to instrument the code a tiny bit. Okay. So whenever you do profiling, whenever you try to see where your hotspots are, you're not running your full program. If you run your full program that takes your 100 nodes and takes 2 days, and you now know where the hotspots were, but it's already done, there's no point. You're going to take a smaller representative case to figure out where your code hits a bottleneck. Okay. The other thing you have to do in Python is to put your code in a function for Line Profiler to attach itself to, so to speak. And then once it's in a function, in front of that function, you can put this decorator, as it's called, @profile. And that just signals to Line Profiler that this is a function you want to know all its line performance of. So once you've done that, you can run it through a command called kernprof. And then these are my favorite options, -l and -v, and then your script name. So just to see how that goes, if I had a script here, this is a nonsense script, although it's valid syntax. If I had a script before that ran and I wanted to know line by line what it did, there's no function here, so I have to create a function for it. So I'm creating a profile wrapper function, put it in there, and then that's a function. In front of the function, I put @profile. These decorators only work on a function basis, so I can't decorate just a line. I have to decorate a function. This is the reason why we have to make a function. And then I call the function. So when I run this, it will call the function and will go into here. And then line profiler kicks in as soon as it sees this add profile, so to speak. So I have to run it through kernprof, -l-v profile me.py. And then if I do that, the output looks as follows. So here's the line again, kernprof -l-v profile me.py. The first part is the actual output of the script originally. And then the profile follows. And there's a time unit. It's microseconds here. And so it tells you the time per line. So here's the code again on the right. Here's the time it spent in the unit, so in microseconds. It also tells you how often that line was executed and what percentage of the time it was spent in that line. So because this is the only function, we know that this is the whole code. And so we can see that 87% of the time is spent in creating this list of about 4 million double precision numbers that are all 1. So that takes most of the time. And then apparently deleting that takes the rest of the time. And the rest is, in terms of time, pretty small. Now, this is a small problem. It won't take much memory, but it's good to know that there is an equivalent tool to test the memory usage of a Python code. You'd want to worry about that because if you run out of memory in any system, then that's bad, obviously. But a number of things can happen that make this a little harder on a supercomputer than on your own system. See, in the best case, your computer goes, oh, I'm out of memory. I'm just going to use the hard drive for that. And it just slows down tremendously. Now, Python was already slow, so now it's even slower. That's not good, but it will sort of go through and you'll notice that, and nothing else on your laptop will work while you're running this. And you go, what's going on? And you check the memory usage, etc. What might happen too is that if you've good limits on your system, your application just crashes. The trouble is that will be the operating system doing that, and all it will tell you is killed. It won't tell you that you ran out of memory. It won't tell you where that happened. It just stops without much information. If it's even worse, if you happen to be on a system that has no local disks, it might try to start swapping or might try and use the memory too quickly, and the operating system panics and starts killing off random processes, crashing your node. This doesn't happen too often, but it can happen, and that's even more mysterious because now you don't even get back that your application was killed. You just get something went wrong, and you don't know. So you should know about your memory usage to prevent these things. Now in Python, you might think that you know how much memory things take, but you can't quite be sure. You're calling functions, you don't know what they're doing, if they're creating temporary arrays or not. You don't know if there's Python objects that you used before that are still in memory. They were never deleted because typically you don't delete your objects in Python. You assume the garbage collector will do it. So the memory is a little bit out of control. So it's good to have a handle on that. And to have a handle on that, we can use the memory profiler package. It does the same thing as a line profiler. It needs the same kind of decorator. So when you have decorated something for the line profiler, you can also run it through the memory profiler. The only thing I will warn you again of is that it does have to check the memory state of all of Python all the time. And if that sounds slow, that is because it is slow. So memory profiler takes a long time to run. You want to make your system even smaller if you can, just to get a handle on where your memory is. But other than that, it works very similar to the line profiler. The invocation is different. Rather than this kernprof command, you just run python-m memory profiler and then profile.py, and that will do then essentially the same thing. So if you run our little nonsense code through here, it will give you the output again of the program, and then it will give you the profile. In this case, again, the code is on the right here, and what it now says, instead of how much time is spent and how often a line is hit, it tells you the memory usage in total as we are going through this code, and how much increment or decrement there was due to that line. So we can see that the line that defines this array or this list of 2 million codes causes some memory allocation, an increment, and the deletion of it causes a decrement. That's not surprising, but we also see nothing much else is going on within the limit of megabytes, right? Within the kilobyte. Like, this has a resolution of kilobytes at most. So yes, I'm creating a string here, but that's not more than a kilobyte, and so we don't see it. Okay, does that make sense? So we're going to do a hands-on, but before we do that, I'd like to see if there's any questions. The line profiler isn't horrible. Oh, sorry, the question was whether this add profile can be left in the code without a significant performance overhead. And so for the line profiler, that is probably true. The trouble is you'd have to run it always through the current prof command, because you can't run it through regular Python anymore with that add profile there. So it is a little annoying to have to decorate and undecorate. In a bigger program, though, that is actually kind of desirable. You might have a few hundred functions and are only interested in one of them. You only decorate that one to see what's going on in that function, rather than having an overhead for all of the functions. So I would really advise not to keep your decorator in there. The question is whether it can measure I/O, and the answer is really no. There's not really a good Python implementation for that. There's ways to try and figure out what I/O does on the operating system itself, but it's a little bit dependent on the system. Sorry, what's the question? For running? Oh, which modules? Okay, so let me show you, because we're going to go into the that leads into the hands-on. So on Cori, you should not forget to source Arzon. You can do the long path, but twiddle Arzon will work as well. HPC pi env / activate. Yeah. Sorry, my source Arzon HPC pi and activate. And so if you're curious what that does, it activates the command, but it's a little bit more than that. It also has a few module commands. So I'm loading the PRG, but there's a whole bunch of modules that are already loaded by default that I'm keeping. So, sorry, module list. So, I don't know where they are. I don't know if that answers the question, but so with Cori, I have had some issues trying to get all of these packages to work at once. So I would suggest you use the environment that I'm providing here. And that's just a matter of not having time to contact the support and figure out what they would advise. But yeah, it's Python. If you have these packages, if you want to know what packages are installed, I don't know if you know the command pip freeze, you can check that too. These are all my my Python packages. Takes a second. Okay, it takes more than a second. There we are. Okay. So if you're curious, and you could actually take this output and install your own Python with exactly these packages with pip if you wanted. But I'm not going to go into how to do packages. I'm going to assume that you kind of know how it is and that this environment is working for you. So we're going to use the code that was there. I'm going to, since it's in my own directory, I'm going to copy it. So the code is in HPC Python. Sorry, you can use twiddle the Arzon for that. And then you would copy it to your own home directory. Since that's the same directory for my directory, I'm going to call mine HPC Python, just because, and then you would change directory, and that should have all your code. I'm already in my environment, so that's good. And so I should be able to run things like the AUC serial.py. And it wants a command line argument. That's the number of points it's going to take for the integral. So it's doing an integral by sampling the x interval. How many points you would take, that's the argument. And so the hands-on, which will try and take about 5 minutes, is to try and decorate this little program with the add profile, put things in the wrapper function because it isn't yet, make sure it still works when you have put it in a wrapper function, and run it through the line profiler, so through kernprof, to see which line causes the most CPU usage. So let me know if there's issues, at least on Cori, and we'll try and look at Stampede quickly. But the code is not that long. It's essentially these lines, and so we're going to try and figure out which line takes the most time, and we'll need a function for that. So I think I'll leave this one up. It's probably the best. This is the hands-on. Any questions before we start the hands-on? So I think this hands-on was as much a hands-on for me to get all the permissions right as for you guys to try something. But yeah, you might have to reactivate the environment, I've heard, but I've heard that it's working now. So let us know if it's not. Otherwise, I think I'll just demonstrate what the routine is, just for the interest of time, and we'll want to get to some more interesting stuff than just this silly code. Okay, so apologies to the VI aficionados, but my favorite editor is still Emacs. I have supporters. I don't take sides, but I do have a favorite. Okay, so we need to put something in a function. The first part of this is just an if statement I'm not really that interested in. It checks that there is an argument. So I think I'm just going to stick to this part, putting that in a function. Let's see, make that. Sure. So how about I put this in a function here? There's various. You could put the whole thing in a function. That's fine too. But let's call it integrates. Like that, and let it have an argument called entot. That's the only thing that needs to be in here, and I can call it with integrates entot. And that should work. So I'm going to test that it's still working. It's always a good idea. Still working. Make sure it takes a bit of time. Good. Not that it matters right now, but this is our timing. And then I have to add the add profile, which isn't too hard now. Add profile. Okay. Should this happen to you, don't forget to resource the environment. Okay, what was I? HPP. Okay, see if it took my changes. AUC serial pi. No. Okay. All right. So running this through kernprof. Let me know in the Slack whether the font is big enough now, because I reinitialized this. Okay, so it ran. It gave the answer that I should supply it with a number. So that was good. So let's run it again. Okay, so it'll tell me now line by line where most of the time was spent. So there's about 20% of the time spent in the for loop, about 30% in calculating y, about 23% in calculating a, and 20% in adding that or increasing x. Good. Just in case you're wondering why it takes 20% of the time just to go over the for loops are not free in Python. They mean that they have, for loops mean that they have to increase an integer. You'd think that would be ridiculously cheap, but not in Python. In Python, integers are of infinite range and therefore are emulated. And so everything you do with integers in Python is inherently slow, which is very strange, but that's how it is. So that's where the 20% comes from in a for loop, and then the rest might have been expected. That makes sense here? But we do know where things spend their time, so good. All right, so let's continue. By the way, you can try profiling the diff2d code as well. It works similarly. Obviously, we don't have time for that in this session, but feel free to do so. Just make sure that you don't that the graphics is false, but I think I checked and it already is. Okay, so what's wrong here? How can we improve this? We know where the trouble lies. We can figure this out. Now let's look at some ways to improve this. So there's a lot of cases where when you say to somebody, especially people that really like Python, my Python script is slow, they will say, why don't you use X? And so we're going to look at a few of those X's. So why don't you use Numpy? It is a faster array for Python. And I think most of you probably, if you have used Python, have used Numpy. So just to remind you or to tell the people that haven't worked with Numpy, why would you work with Numpy arrays rather than just lists? Python has lists. If you want an array of things, you just put them in a list. And that's because Python lists aren't the ideal type to do basically scientific computing with. They can do funny things that you might not expect, especially if you're coming from a language like Fortran. They do weird stuff. So I've got some weird stuff on the right hand side here. I have an array, or I should say a list of 4 numbers, 1, 2, 3, 4. Here it is, A. Another list, 3, 5, 6. It's called B. And I'm going to multiply A by 2. 2 times A. If I came from Fortran, I would expect something like 2, 4, 6, 8. Rather than that, I get the list twice. 1, 2, 3, 4, 1, 2, 3, 4. A list times 2 is twice the list, is a list and a list appended. That's what Python thinks of when it's using lists. A similar thing happens when you add 2 lists. If I add A plus B, it doesn't add them element-wise. It just appends one to the other. Again, from a list perspective, it's not so strange. I have a list, I want to add another list. Obviously, I get a bigger list. So lists aren't arrays. And so that's one reason why they're not ideal for scientific computing. So arrays are a much better choice, but they're not native to Python. Now, that's been solved by Numpy. Numpy offers a data type that is an array. And so you can have a whole bunch of different arrays, but the main thing of the arrays is that they will do element-wise operations, but also an array can only contain one type of element. So a list could have the first element be a string, then an integer, then a float, and Python has no issues with that. But that means that every item of a list comes with a descriptor telling Python exactly what type it is. Which, as I mentioned, kind of gets in the way of streaming through a bunch of data. Arrays are supposed to be different. They're supposed to have one type for each of the elements. And so while they can have any type, they all have to be the same. So the arrays contain the type descriptor only once, if you want, and then can run through a consecutive set of numbers or strings or what have you. So ways to create them. So NumPy, you can import anything from it. Zeros will create arrays with zeros. Ones will create arrays with ones. You can have them have a shape. So here's a 2 by 2 matrix with zeros. You can make ranges. Here's a range from 0 to 4. The number that you give to a range is the one that you don't get. That's how it works in Python. Linspace is a little bit funnier but handy. It gives you a range from 1 to 5, including 5, although you don't see the 5. The 5 is included. And then you can actually say how many points you want. So here's a linspace from 1 to 5, 1 and 5 included, with 6 points in between. It's very useful if you think of wanting to create a grid, which is kind of what we will want to do for the integration example. So nice, we have arrays. We can use them, just import NumPy. The other thing that is really good about NumPy arrays is this element-wise arithmetic. So, so we're going to call them vectors. It still bugs me to this day, because I have a mathematical physics background originally, to call something that is just a list of numbers a vector when it doesn't transform under the Poincare group as it should. Be that as it may, that's an in-joke for the physicists. Vectors and arrays are interchangeable. So a vector and a vector, you can add them, and we will, in this context, mean an array can be added, and they'll be added element-wise. So here's an array. Here's another array. When I multiply them, it's element-wise. When I add them, the same would happen. So here's a case where we have sort of the fortran idea of an array. I have an array. They're of the same size. I multiply them. Each element gets multiplied, and I get a new array. That works. Now, if you do want these to be treated as regular linear algebra objects, and you want an inner product rather than a product element-wise, there is a special operator in Python. It goes by the @ sign. That's been introduced only since Python 3.5. If you have something that is less than that, there's a dot method. So you can do mp dot. I don't know if that makes sense. There's a dot function that you can use instead that does the same operation. But that's the way you would do an inner product between two vectors. Okay. Nice. We have that. The same is true for matrices and vectors, but this is a little bit funny now. You would think that the matrix times a vector can only be a linear algebra product, but this is not true at all. Python does a product of a matrix times a vector by basically doing an element-wise multiplication for each row. That's what happened here. In linear algebra, what we would mean by a matrix times a vector is this particular expression here. And one thing that you would see is I return the matrix here. You can kind of see they went wrong, and return the vector here, which is what a linear algebra would say. So when you're doing linear algebra with NumPy vectors, and matrices, that's fine. You can do it. Just make sure you use the right multiplication operator. And then finally, the same is true for matrix multiplication. It's actually even trickier. If by accident you use the wrong operator, if you use a star, you get element by element multiplication. Whereas if you meant matrix multiplication according to the rules of linear algebra, you would expect to get this. But in both cases, you get a matrix back. So you don't really see it unless you actually check the results that you've made a mistake. So this can be tricky. If you want to be very, very sure, maybe it's a good idea to use the dot function anyway. So you're very explicit and you can't make a mistake. So that's that. Arrays, all the same element. We can do linear algebra. We can do element-wise operations. Those are nice things to do. Now, because they're now just one type, they can be streamed. And so you would think these are now faster arrays than my Python list. So let's check that. So we will look at our 2D diffusion equation. It's a pure implementation in Python. We ran it before. It's 642 seconds. So I would advise not to run it right now. Because you'll wait until the end of the session almost. But you'll have to trust me that this is how long it took on Blue Waters. And I changed my lists to NumPy arrays. I've called it diff2d slow NumPy. Wonder if you can guess why. So I ran it, and now it runs in 1678 seconds. So that didn't really help at all. So what gives? Aren't NumPy arrays faster arrays? So let's look at the code, see if we can get an idea of what's going on. So here's the code again. Remember, it fit on one screen. It's the same code. The only thing I changed, instead of creating lists here, I used linspace and some zeros to initialize my density matrix or my temperature matrix. And other than that, because it's the same, you can use the same syntax with NumPy arrays as with lists, which is very convenient. The rest just looks exactly the same. I switched off graphics, so it's not that. It's not more expensive to plot a NumPy array than a list. That's not it. But if you look carefully, there's a bunch of loops and indices and stuff. Lots of for loops. I've already told you, for loops are not free at all. What's going on here? Like that's we should look at those. So that's what's wrong here is not the fact that we used the wrong data type, but we're still using element by element indexing. And so if you think about why that matters, is that because Python's overhead mainly comes because every line is interpreted. So whenever I have a nested loop like I have here, this line gets interpreted n steps times n row times n columns times. Reinterpreted, 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 reinterpreted. Then it has to check this line, it still has to check where I and j lie, and then can do something, right? So we can't. So the fact that these things are now nicely aligned in memory doesn't really matter if we still have those for loops and we're constantly just interpreting a Python code. We want to do something, use those arrays as full arrays, so that NumPy behind the scenes can do its magic. So that's kind of called element-wise vector operations, as we just saw. And so we're going to have to try and do that. So what I mean, just to give an example, is that if you, instead of having, say, 3 arrays, A, B, C here, one is a linspace from 0 to 1, and from 1 to 2, they have 101 elements. Suppose I wanted, for the first 100 elements, just to element-wise add them, then this code will work for NumPy arrays. But this line is interpreted 100 times. What I should do instead is use the vector operations, use the element-wise operations, and say C equals A plus B. It'll do the same thing, but it'll only have to interpret this line once. So from the interpreter point of view, this is 100 times faster. Now, this is a small array. If you test it, you won't see it because the startup time of Python will completely overwhelm any timing. But this is the way you should think of this. I have an array. I want to add one to the other. Don't think of the elements. Think of the whole thing. Now, this doesn't always work as nicely because sometimes your arrays aren't lined up. So, for instance, if you had a situation where Ci, the ith element, should be the ith element of A plus the I plus first element of B. How do I do that? And so here's where, so you have basically a shift in one of your arrays. Well, what you should use is this slicing mechanism that you have in lists, but also in NumPy arrays, to index a part of the array. So rather than doing this by hand, you say, okay, I want to take the first 100 elements of A, which is what's happening here, and the last 100 elements of B, which is what effectively is helping that, and add those. These separately, these slices are 100 elements long, and so they can be added element by element, and I store that in C. Again, there's only one line here, so there's only one interpretation necessary, rather than 100. So even when things don't exactly fit, you can often still express it using slices into something that is of a more vectorized form, if you want, using whole vectors, whole arrays. So we're going to try this. This is going to be the second hands-on. We're going to take about 10 minutes to try and take our serial AUC code, remove any decorators, and try to see if you can come up with a way to do this with whole NumPy arrays. There's a for loop in there. We already saw the for loop was a little expensive. Let's see what we can do to improve this. Make sure you use whole vector operations. And measure the speed up with the time command, or if it doesn't find the time command, although it's fine on Cori /user/bin/time. Okay, let's try that. Any questions before we start trying this? Anything, Marcelo, did you think I should address? Yeah, whenever you can have less interpreted lines, that will be better in terms of performance, obviously. Okay. Put 10 minutes on the clock and see where we get.
Ramses, did you get the question about rephrasing, why the slower versions are slower compared to the new version?
Oh, no, I didn't see that. Okay, so why the NumPy arrays are slower than lists? Lists are native to Python, so Python really still knows more about the list than it knows about those NumPy arrays. So I don't have a full explanation, but I guess there's just more overhead trying to call the NumPy functions than something that's already baked into Python. So it is kind of surprising that it's actually slower, but I think it's because it's an external package more than anything else. All right. So let me show you what I would do. Let's hope I keep my connection this time. I'm going to remove the profile first and keep that in serial so I can time things. Forgot how many zeros I had here. Python. Okay, it's not bad. And then let's copy this to a new file. I think we just have to call it vector. And right. So it's a little bit funny because there were no lists initially or arrays initially. So we kind of have to invent them. And so what I would do is I'd say, okay, we want a whole bunch of x values ranging from 0 to 3 with a total number of n tots. So let me create a lint space. But before I can do that, NumPy as NP. By the way, if you're not used to Python programmers are lazy typers. They'd like to abbreviate every package under the sun. NumPy is almost always abbreviated as NP. So I can do an NP lint space. What did I do now? Strange. About that. This is my terminal application malfunctioning. Okay, let's see. What did I say? Okay, so import np. Okay. np lin space from 0 to width, might well use that, and a total number of points of n tot. I'm going to gloss over the fact that whether it should be n tot or n tot plus 1, I'm not too concerned with that right now, but you should be if you want full reproducibility. And so we're going to have to, so here's our x. This is fine. Now we want to compute y, so we could go over the x lint space and do a for loop or just a loop over x and compute y in this way. But nice thing about NumPy is that you can use the expression that works for a serial number for a scalar and use it for a vector. So here are all my y values. Great. And now I have to sum them all up and multiply them by the x. So I will sum them all up and multiply them by dx. And a little bit of luck, this will work. So I've got a lint space, y values, I'm summing them up. I think it works this way. Right. This is not. Okay. This is not a good sign. Right, that's a little bit better. When you get in the realm of seconds, especially with Python, the startup time can vary a lot on what other people are doing on the file system. So I should probably have a bigger size sample. This is one vector serial. Right, so that's not bad. We'll leave the diffusion equation for yourself to do. So for the diffusion equation, I did the same kind of thing. I didn't have to create an array; they were already there, and I got 100 times speed up with the diffusion equation. With the area under curve, which we just did, I got about a 17 times speed up for this. Was on blue borders. Now somebody mentioned that we're taking a lot of memory to do this, and this is true in principle. We're creating the whole array. So from a memory perspective, this might seem inefficient, but from a CPU perspective, the 17 times speed up is not. So it's all about maxing out one versus the other. If you have that memory to spare, might as well use it. If this didn't fit in your memory because it's that big of an array, then you'd either have to chunk it up until you fit it in memory, and you'd have to play that balancing trick. But in this case, I'd gladly pay this memory penalty to get things done 17 times faster. So I'm calling this vectorization. I've called it a few times. When some people talk about vectorization, this is not what they mean. They mean using the SIMD units in your CPUs that can compute several additions and multiplications at the same time for a couple of numbers. It's not quite what we're doing here. What we're doing here is vectorization in the sense that we're operating on whole vectors. And that is a great benefit for Python because we're not interpreting lines over and over again. Now, Numpy might be compiled such that it uses the CPU vectorizations, or it might not. That depends on your implementation, whether it calls certain blast routines under the hood, but that's not really that's too much detail for now. In this case, we're still going to call it vectorization just because it's using whole vectors rather than anything else. And using that, if we didn't use that, we couldn't even hope for the implementation to use the CPU vector units at all. So it's sort of a prerequisite anyway. So I'm going to keep calling it vectorization, although it's not entirely the same as using the CPU vector units. Okay, so the diffusion was 100 times faster. That's fantastic. We do have to keep in mind, though, that the compiled versions were still about 5 times faster. And a similar thing happens for the area under the curve. Actually, something worse happens in those cases. It's much faster. But now, actually, the compilation of these things of the compiled code for the area under the curve takes longer than the actual run. So if this is, but still, from the point of view of having now a Python version that is still very Pythonic, just works on whole arrays and with NumPy arrays, we've gained a lot, and we can be pretty happy with that. Okay, so let's look at the next. But why don't you just use this? So the next X. So people say, oh, that you complain to, they say, oh, my Python is so slow, or can't it be faster? They said, why don't you use Cython? And so what is Cython? Cython is a compiler for Python code. So that sounds fantastic. It was the fact that it is not a compiled code that made it slow, wasn't it? And so Cython, by design, is such that any valid Python code is valid Cython code, almost. That's great. I can take my Python code, give it to Cython, it compiles it, and it will run it. And so I've tried this, and it's a little bit complex to get it to do this. So I've done this. Now to do it yourself, if you want to try it, you need the Numpy version of diff2d. So if you want diff2d Numpy, there's a file in the code directory called on_with_the_show, which is secretly a zip file. If you unzip that, you will now have that file, and it'll need the Numpy version. Okay, so then there's a special make file to compile the Cython version of it, and then we can run it. So there's the Numpy version here that comes from on_with_the_show, and it takes about 5 seconds. And then here's the Cython version, and it takes 9 seconds. And so I'm doing this on purpose. We're not going to go into Cython for 2 reasons, but one of the reasons is that it's not automatically faster. Just as using NumPy arrays is not automatically faster. And the reason is kind of tricky. Because valid Python has to be valid Cython, by definition, everything that Python does with their arrays when it's doing its business, Cython does the same. It's just compiled rather than interpret every time. So you do gain something, but it still has to do reference counting. It still has to check types for every element. It still has to do all these Pythonic things. It still has to do garbage collection. All of these things are still done by Cython, unless you go away from Python equals Cython. So to get to true performance in something that is closer to compiled languages, you have to use Cython extensions. Now you're not really programming Python anymore, and sometimes those are small modifications. I know that. You just have to say this variable is this particular type, and etc. So it's a possible avenue, but you leave the Cython realm, and so I'm gonna not focus too much on this. Mostly what people use Cython for is to write extensions, in other words, packages for Python. And it can be very useful there because you only have to do this translation into Cython once, and it's close to Python, so it's easier than rewriting it completely in C. You write it in Cython, and then you have a package, and you just call those functions again. That's great. That's a good use case, but you're not going to take your scripts, your Python scripts, run them in Cython and see any performance benefits unless you rewrite them into Cython, and then you're rewriting them already. Does that make sense? All right, so I would say that we've done about as good as we can with getting performance out of Python, and we're only a factor of 5 off. If we can write our code, let's say, in a week rather than in a year, and it's 5 times slower, I'd say that there's a case to use Python in those cases, right? So now that we are at the point where we might say we have acceptable Python performance, we can try and parallelize things. So we're going to look in the rest of the session at parallel Python. And here too, there's a lot of packages that promise to do things automatically. Why don't you use X? And I can't actually look at all of the X's. The truth is, it always depends on your use case, whether it works or not. We have 2 use cases here, so these are ones that work for them. So I'm going to focus on 3 and mention a 4th. NumExpr, an old package that can do some sort of threaded parallelization, multiprocessing, which can create multiple processes doing separate things, and MPI for Pi. Now we've seen MPI in great detail. You can do MPI in Python. And it works similarly, but simpler. And so we'll leave that to the end, because even if we, for some reason, run out of time, those are things that are fairly easy to read on your own. Okay, so let's look at NumExpr first. So it's a package, Python package, and it's useful if you're doing matrix algebra. Basically, if you're doing anything like vectorized NumPy expressions. And it's kind of a just-in-time compiler isn't quite the right word for it. It's a compiler for NumPy expressions. You can suppose you had a NumPy expression, so a vectorized expression. You give that to NumExpr, it compiles it, and it doesn't just compile it compiles it in a way that it can do that it can use multiple cores by doing threading. And so that is almost trivial, you would think, if you have element by element operations and it goes into a new array. Each operation is independent, so of course you could parallelize this, and that's what NumExpr does. It takes a matrix expression, breaks it up into chunks to give to each thread, lets each thread do its thing, and then gives you the output. That's nice. It's fairly simple, and in some situations can very easily but significantly speed up your calculation. So let's see how. Now, I should mention that it seems a little strange, perhaps, to use a package to do threads. In C and Fortran, we just use threads or OpenMP. You can't do OpenMP. Even if you in Python for various reasons. But one of the reasons that it's not a very good idea, even if you could, is that Python has threads. This idea of having separate execution threads that can run at the same time. You could have a thread taking care of the visualization while another thread is doing more computation. Stuff like that could happen. But it turns out that at least almost all of the Python application implementations that you'll be using can only interpret one Python line at a time. So even though I can have multiple threads with different Python codes being executed by each of them, I can only interpret one line at a time. So that means that if most of the time, if there's not much work to be done in it, most of the time is interpreting that line, I am essentially serializing my execution. I'm interleaving the execution. So it doesn't give you any performance benefit. And usually when you think of large-scale computations, you're in that situation. I know there's cases where you can get around that, but they're not all that typical. And if you have your own Python code, threading is just not going to help you. It's just going to make it slower because now the interpreter has to switch back and forth between contexts, and it's not good. So that's why we're not using Python threads for scientific computing, where you have the same little things to do for a whole array. This thing is called a global interpreter lock, and it's still around, and unfortunately makes native threads in Python not particularly useful for performance. They're very useful if you want this sort of simultaneous behavior, where you might have a GUI that still reacts while the computation is going on in the backend, but it's not using more cores. Okay, so NumExpr then, which we are going to use, is insanely simple. And that's its strength and its weakness. You give it an array expression like C equals A plus B. It will compile it, it will run it, it will give the output, it will have run in parallel over how many threads you set it. It can do additions, subtractions, multiplications, divisions. All of these operators are supported. It can do a whole bunch of functions too, like sine, cosine, tan, a whole bunch of them. It can do simple reductions, like taking the sum of a whole array or a product of a whole array, although in those cases I found usually not summing the array with NumExpr, but just with NumPy is usually just as fast, if not faster. But the element-wise stuff is really good. Right, so how does it work? So here's a serial version. I'm taking two arrays, A and B, with random numbers. I'm filling another one with zeros, and I'm going to time things. So I have a little function that just measures the elapsed seconds, kind of like the time command. And I'm going to compute A squared plus B squared as arrays plus 2 times A times B for no particular reason. And this takes, according to the timing, 0.11 seconds. It's not a very fast, a very long calculation. I might get better scaling if I had increased it a little bit, but this is what I had. Okay, so if I want to use NumExpr, I first have to import it. And again, I'll abbreviate it to NE. And I can tell it ahead of time how many threads it should use. So let's start with a serial version. And we'll do the same thing. And the only funny thing, not the only funny thing, one of the funny things about NumExpr is it wants its expression as a string. So I've got it here just written as code, and I have to put that code in the string. It's a bit silly, but it has to compile it. Sure. So NE evaluate will take this string, not interpret it, compile it, use several threads to run in it. In this case, one thread, and then we'll see, and it gives the result. So in this case, it takes 0.058 seconds. So it's already about twice as fast, just from the very fact that it's a compiled code, which is kind of funny. And it depends on how your NumPy arrays are behaving. It depends a little bit, but that's funny. Now we can add more threads, and you'll see this go down. So I added 3 threads, and it was almost perfect, not quite, factor of 3. And then the more threads I add, the less increase you'll see. So it kind of stuck at this element. That's it. So this works almost for free. I have an expression. I just give it to numexpr instead, and it gives me the result faster. Fantastic. So we're going to try that. You already have your vectorized code, hopefully, because we're running a little late. But let's just try it for 5 minutes and see if it works. But this will only really work predictably if you got yourself a code, some resources from the allocation, from the reservation. Otherwise, if we're all doing this on a similar login node, we will get very fluctuating results. But still nice to see. So copy the vector to numexpr, and then try importing numexpr and run the code that we had, and run it through numexpr and measure the speed up if you use, say, 8 threads. See what goes. So let's do that for any questions about what I'm intending you guys to try and do. So this one shouldn't be very difficult if you got your vectorized stuff to work. So let's again copy AUC vector to AUC numexpr. Oh, I already have one. If you don't care too much about setting the number of threads, it's actually as simple as adding numexpr and chasing our line y equals 0.7 times x cubed, etc., to y equals any dot evaluate. And that's the only change I really have to do to make most of the change, most of the effect. And so, it's kind of weird because it's now a string. But that's okay. I think we can try with our vector here. Okay. I'm doing this, I did not ask, and I won't right now, for part in the reservation. I hope you did. We'll get more reliable answers. But it should take slower. So it's faster. Should again take us. Sometimes, I don't know if you remember, things scale better if you make your problem size bigger. So let's try that. Vector. Yeah, not bad. I think it's using something like 4 cores here, but I'm not entirely sure. We could set that, but you get the idea. Okay. So that's good. That speeds things up. You will have noticed it even speeds it up when it's just compiled, and there's a reason for it. Compiled code can just pull tricks that Python can't, and so it's pulling tricks. I don't know which ones those are. That's up to the compiler. It's a bit of a mystery. But that's what it is. A few things that are annoying when you want to use this in other codes, like the diffusion equation I should mention, is that numexpr is very simple, and that's good. That's why the reason it can be so fast, but it has no facilities for things like slicing or offsets. And so that's annoying for the diffusion equation, because that's what we need. If you look at the NumPy vectorized code for the diffusion equation, you will see an expression like this, where we take our density or temperature field in different spots, and we shift them just so that we get the stencil right. And the shifting we cannot do natively in numexpr. So you need to apply a trick for this to work. And now it becomes a little bit cumbersome. You have to make some sort of a view on the density array that looks like a regular array, except it's somehow still shifted. And so I'll let you figure out those tricks by just looking at the code yourself. Even if we do that, though, it turns out that the effect is pretty modest for the diffusion equation. So again, these were Blue Waters timings. Things could be different from on a different system. So the Numpy array already gave me 5.6 seconds. I add 8 threads of numexpr. There's, by the way, this is the environment variable by which you can externally control the number of threads that numexpr use. So that is useful for scaling analysis. And I run it again. And in this case, it takes 4.7 seconds. Now, it's quite possible that we're not seeing the full effect, partly because it's a small run. A good bit of this is just loading in the Python libraries, which isn't going to get any faster. So that's, and if you want to know how I did it, you can look at diff2d numexpr. It's possible, but it's a little bit tricky. The reason it's still sometimes advisable is that the difference is already in just making this compile, but the compilation itself better be quick. Because every time I hit that numexpr line, if that is in the loop itself, and that's one of the things that happens in the diffusion equation, if that happens, then I have to compile it over and over again. So the compilation has to be fast. The simpler the syntax that it arrives, that it accepts, the quicker the compilation can be. So one of the other things that people will throw at you, it's a little bit newer, is, okay, your Python code is too slow. You don't want to use this old numexpr. You can't even pronounce it. Use Numba. It's new. It's fantastic. It runs on the GPU too. And so why don't you use Numba? So I tried this. The fact that there's only 2 slides on it will tell you the result. So timing it for the NumPy is 4.5. For Numba, 11 seconds. What I had to do to the code isn't terribly difficult, but I had to take the most expensive lines, which we would have found out by profiling, and put them in a separate function. Fine, not a bad idea. And put a decorator in front of it to tell it to compile it, essentially, or really to do a just-in-time compiler of this code. So that's what Numba does. It does a just-in-time compilation. And that is potentially very, very useful. Just not so much in this case. In this case, really the overhead all goes to the compilation. And so it's not substantially slower. It's not that that's terribly bad. But in this case, it's only it's just not doing it. So I have nothing against Numba. This is how you would use it. You would put your most expensive parts into a function, and you would compile it. You can read up on exactly what Numba can do, because it has way more capabilities that say numexpr doesn't have. You will see that all my slices are there, so it's potentially much more powerful. But you sort of pay for that power by having a more expensive compilation step. And so I think that's what we're seeing. You should know it. You should try it. All these things, you won't know if they help you unless you try it. And so I tried it. And in this case, for this one, it didn't work out, but that doesn't mean it won't work out for you. So one that does, well, okay, so let's look at a few other things that one can use in parallel processing or parallel programming for Python. So another avenue, which doesn't really fit very well with the things we were doing for the diffusion equation, but it does for the area under the curve, is called multiprocessing. Again, it's a package. And multiprocessing is kind of funny. I told you there's no threads in Python, or no concurrent threads. That's true. But some people really like working with threads. But the very original way to program threads is to define a function, create a thread, give that function to the thread, run the thread, ask if the thread is done, and then continue. It's very like there's no nice work sharing or anything. It's just launching threads and having them do things. And so multiprocessing, instead of launching threads, does the same thing but with processes. And so the difference between a process and a thread, I don't know if that's been fairly clear to you, but threads run within a single process and they share the memory and the resources of that. And in the current context of Python, that means that if I have threads in a Python program, they all share the same interpreter. But if I have several processes, Python processes, each of these Python processes has their own interpreter. So they might have a lock for their interpreter, but they're different, so they can run in parallel. So that's a trick that multiprocessing pulls. It creates, instead of threads, it creates processes. Now, processes are a little bit more memory hungry. It takes a little longer to start them up than it does threads, but they can run in parallel, so that makes up for it. And so that's what multiprocessing is all about. It's very similar in syntax to threads that you would otherwise use, but you use processes. Another nice thing about it is that it's implemented in different operating systems. How you launch processes in different operating systems, Windows, Linux, Mac, it's all different. And so this abstracts that out as well. So just as an example, here's a function that returns the square of things. I'm giving it a list. And for each of the elements in the list, I spawn, that's how they call it, a process by starting it and adding it to a list and waiting for all of them to end at the end. It's kind of laborious to do this in this way, but that's the model. You spawn off different ways. Now, it's been realized that this is a little laborious. You just want to basically have these 10 tasks spread out over different processes that then hopefully would run on different cores. And so for that, they have a work sharing construct. This is kind of the closest that you get to OpenMP kind of behavior in the form of a pool object. So multiprocessing as a pool object. That essentially, you can think of it as a pool of threads that's ready to do stuff, and then a way to map cases onto different threads. So this is good if you have data parallelism, if you have the same thing to do for I would just, never mind the Slurm one. You have a number of processes, you create a pool with a number of processes, and then that's a list, if you want, of pools of processes, and then there's that list has a map function. So P is a list, or a collection of processes, a pool, really, and on that there are numprox threads in it, and I give it a mapping function, f, so that's still a function, but that function gets applied applied to a range of values, but that range of values is chopped off and given to different threads. So it sort of automatically work balances. And the nice thing here is that I don't have to spawn them separately. I can change the number of processes. I can change the size of my list, and the syntax doesn't have to change. I don't need a for loop to spawn them. I have my threads. I have a list. I have a function to apply, and that's what I'm doing. There's a lot more to multiprocessing, and I really don't have the time to go into it. It gives the answer. That's good. So there's ways to have shared memory with multiprocessing, which means that you can now have race conditions in Python. So that's good. And you can have inter-process communicating. There are ways to do jobs over multiple machines, multiple nodes. There's events, there's conditions. There's a lot to this module, which is great, but I'm going to leave that for yourself to explore. Any questions about that before I go to the last topic? So then finally, I want to make contact to a lot of the other stuff that happens in HPC, MPI4Pi. And so MPI4Pi is a Python wrapper around the MPI library. And here it is really nice that MPI is just a library. In C and C++, you include a header and you link with the MPI CC command or something similar, but it just links to a library. They're all function calls. And so there's no problem once you have a library to create an a Python wrapper around it. And so that's what MPI4Pi is. So it can do everything, pretty much everything that MPI can do, point-to-point communications, so sends, receives. You can do collectives, broadcasts, gathers, what have you. It has a facility of optimizing Numpy array communication. And the reason that it might have to do that, or you might want to do that, is that we'll see that in a second. But by default, the communication has some overhead to do MPI in Python, but you can get around that. So how would you work with MPI4Pi in a nutshell? And if you know MPI, most of you do, there's going to be some familiarity and some things where you're going, oh, does this work like magic? And the answer is yes. So if I want to use MPI instead of importing it or using the MPI module, I import MPI out of MPI for Pi. This does, if I just import MPI for Pi, I can do that, but it doesn't initialize, doesn't do an MPI init. If I import MPI with capital, it does an MPI init for me. Boom, done. And then the communicator exists. By default, there's an MPI com world. So in this case, it's MPI.com world. The difference between MPI for Pi and regular MPI is that MPI for Pi is way more object-oriented in the way that it's written, and so the communicator is part of MPI. I like to give that a name because it's a really long thing to write, so I just call it com, but that has no other significance than just abbreviating it in this case. Okay, so I've got my communicator. Now, in MPI, whenever you start MPI, all of the processes are starting at once, right? That's the canonical way to start MPI. So suddenly I have 100 processes, and they all run the exact same code. That is no use because I want to run one thing. I don't want to run one thing 100 times. I want to divide things over the space or whatever. So the processes themselves in MPI always have to figure out who they are. Where are they in this list of processes? And depending on where they are, they can do something else. So where they are, that goes by the name of the rank. So you have a rank from 0 to n-1, where n is the number of processes. And you can get that from the communicator. Inside the communicator, you are a certain rank. How do you get it? com.getRank. And now that I know there's a com.getSize as well. Now that I know my rank, I can start sending values to other ranks. And so what's nice is that I can just take any variable, doesn't matter what it is, some Python variable, and say send it to a certain destination. And what you see from the syntax already is that you don't have to specify what type variable is. Things like tags and that kind of stuff is optional. So if I'm okay with just tags all being 0, fine. And I can just start sending things to another process. The reason, or this flexibility, that's where the cost is. It comes from. This variable has to be somehow sent over. If this is a list, I have to somehow know how big the list is and send that over. So there's a way to create what's called a pickle out of any Python variable. And it used to be used just to store things on disk. You pickle an object, you store it. Could be a list, could be a whole bunch of, could be a map, could be a dictionary, could be anything. A dictionary of lists of dictionaries. You pickle it, it becomes some sort of string representation that could be dumped to file and be read in and be exactly the same. So it uses that same functionality here. It pickles the object that you want to send, sends it over, and then the other end it gets unpickled. That's the overhead. It takes some computing to pickle things. Anyway, it's sent off, and then the other process can try and receive it with com.receive. It can say where it wants to receive it from. If it doesn't say that, it's like an any source, so that it can be even simpler. And what's nice, because this is a dynamically typed language, is that I don't have to have a buffer ready for it and say how many elements it is. If I receive it and I put it in a variable. If it's a list of 100 elements, variable will now be a list of 100 elements. If it's a list of 1,000,000 elements, variable will now be a list of 1,000,000 elements. I didn't have to pre-allocate things. It's very flexible in that sense. You do still have this idea that you have to match your sends and receives. You can do one-sided communication if you want to get around that, but the same deadlocks that you could have in any MPI process, they're still there. There's a send receive to help with that. So if everybody is sending something and receiving something, usually a deadlock is a concern. You can do send receive. So there again, you have a send variable. You send it to a destination, but you want to receive something from another destination, from another source, and that then gets returned. You can do collectives as well. So you can do reduces. Here's a reduce of a value. Every process might have a value. We want to add it up and give the end result to the process with rank 0, and then that's what's happening. So this, and I already went over this a little bit. One of the annoying things about MPI is that it's a library, and the library doesn't know about your variables, and because it doesn't know about your variables, it doesn't know what type they are, or how long your lists are, and you have to specify that. You have a dozen arguments to every MPI call, right? It's fine, but it's annoying, and it is why nobody knows the order of all the arguments in MPI. Even if you're a seasoned MPI programmer, you have a call that you haven't done for a while, you're going to look up how it goes. And that's because there's no way for the library to look back into your C and Fortran code to see what type these are. It is known to the compiler, it is not known to the library. So Python changes that. With this layer of MPI for Pi, you can look at your variable, say, hey, this is a list of 100 elements. Good. Now I can call the real MPI library, make a data type, or store it in a pickle, and the pickle is X bytes long, and send it off in the right way. Right? So that's why Python is different. It can look at its own variables and see what they are, and then call the library function. So that's why code in MPI for Pi is kind of more easy to read and easy to write too, if you don't mind paying a little bit of this penalty. So here's an example of a code that sends, so we've got n processes, and every process determines its rank and sends it to its right neighbor. And so I'm importing MPI, that's my MPI init, I'm getting my rank, I'm getting my size from the communicator, and from that I figure out who is my right neighbor. Well, it's the one with rank +1. I'm doing periodic boundary conditions, so the right neighbor of the rightmost element is element 0. And the same with the left, but the opposite way. And then I can do a send receive. I'm sending my rank to the left, and I'm receiving it from the right. And then whatever I'm receiving from the right, I store in my variable rank R. Because I'm using send receive, there's no deadlock here, even though it goes around in a ring. And that's it. And I'm printing out what it is. So it's kind of nice. It's a very nice way, especially if you're sort of prototyping an MPI algorithm. This can actually be quite useful, even if the performance of the actual computation might not be. So we're running out of time, so I guess this last hands-on is a take-home or take to the lunch. You can ask me questions on the Slack. I'll look at it. The idea is to take our vectorized area under the curve. You could take the NumExpert part as well, but I didn't want to do hybrid. Take it, and now you have to do your typical MPI stuff. There was an array. We're going to have to chop up the array, have every process figure out what part of the array it's going to work on, do all of that sort of domain decomposition, divide the work over the MPI tasks, and then see if it speeds up. It's very similar to any MPI. It tends to, if the problem size is big enough, it tends to scale quite nicely. Actually, MPI for Pi almost always scales better than MPI in C or Fortran, because the relative price of the communication is less because the computation is so much slower. If your computation is 5 times slower, relatively speaking, your communication is 5 times faster, and so your serial fraction in the Amdahl's law is effectively smaller. It's not a real effect. Your Python is still slower, but it is kind of nice to show sort of theoretical scalings and this, make pretty linear plots and things like that. So speed up tends to be good if you still have some overhead, but it's good. Okay, so I'm going to leave that and just finish up. Leave that for, I guess, either the break or do it another time. And as I said, I'll keep an eye on the Slack. I've kind of talked about this. You can circumvent the serialization, the pickleization. If you have NumPy arrays, they have to be fairly big for this to really make a difference. And now you're back to having to have buffers and stuff. So this is sort of an optimization you could do after the fact with NumPy arrays. GPUs, it's not talked about GPUs at all in here, which is unfortunate, I guess, but no, I only have 2 hours. You can use GPUs in Python, but you have to curb your expectations a little bit. You can do sort of a CUDA equivalent in Python called PyCUDA. What you're doing then is essentially writing CUDA kernels that you can call from Python. That is great. If most of your time is spent in that kernel, you'll get fantastic speed up. But if most of your time is still spent in the Python code, then that doesn't really help you much. And then there's packages that try to sort of automate this or make it simpler. And Numpy is able to run on the GPU for certain functions. As I said, Numpy takes a function and then calls and then just in time compiles it. You can do that for GPUs as well, but only for a restricted set of the syntax. So, which are exactly the kind of things that you think you can do with CUDA. There's QPy, which is cute and interesting. It's an array. It's a replacement for NumPy arrays, with arrays that rather than live in CPU memory, they live in GPU memory, and all the operations are done on the GPU. And I've played with this. I couldn't get it installed on Cori, unfortunately. But it can be nice. But here too, you have to realize it's still not going to beat your compiled code on the CPU for most cases. You still have your Pythonic part in there. Other cases where GPUs can be useful, if you're using things like TensorFlow or other AI packages that behind the scene call optimized GPU stuff. In that case, that's the way to go. Like if you're doing machine learning, if you're doing neural nets, you want to use things like TensorFlow or Keras on top of TensorFlow, and have their training run on the GPU, and that's exactly how you should go. In that case, all of your pretty much all of your computation is on the GPU. And the fact that you're running it from Python doesn't matter. So that's the hope. So pure Python in HPC, is there any hope? No, you shouldn't do that. And with HPC, I mean anything that runs at scale. There's no right, but there is some hope. If you're doing data analysis, if most of what you're doing is reading in a file and parsing that CSV and doing simple operations and writing it back out, that's not going to be any faster in C or Fortran, right? It won't be, because most of the time you're waiting for the disk. If you're using optimized packages like TensorFlow, or then again, you might not be spending all your time. Your code might not be spending all its time in Python, but in the library. Then again, you're fine. So it depends on what you're doing. But just as a computational language, no. But as a tool to interface with things that are already optimized, sure. I think that's the end of my story. I'll take some questions if we have time, but I think officially it's lunchtime. Okay. Sure. The question is, do I have any comments about Dask? And so Dask is good. I put it in here somewhere, I think. It's good if you have, so what is Dask does a very different thing from the things we're looking at. Usually when we do parallel programming, we know what we want to compute and we divide it up and we give it to processors. Dask is a little bit different. You kind of describe what you want to compute. It makes a graph out of it, and it sees what part of the graph it can do in parallel. And so it's a very different approach in that sense. It can build up on top of multiprocessing as well, so you could run this across nodes. And so if you have a lot of tasks, but the tasks themselves are fairly heavy, so not adding 2 elements of arrays and putting it in a new element, that's going to be overkill. But have something that's a little bit more heavy, then I expect that to do very, very well. So the question is whether what the difference in speedup would be using the NumPy vectorization and the a multi-threaded blast call. Yeah. It depends on what you're doing. In this case, we're kind of linearly going through the array. I mean, it goes around, which means that it all depends, I guess, on like when you're using blast calls, whether they optimize it depends on how much computation is happening in there. In this case, I think you wouldn't see much difference because the amount of computation I have to do per element is kind of small. So I wouldn't expect much, but it's anyway. I don't know if that makes sense. So the question is, other packages, PySpark, PyOpenCL versus PyCUDA. So PySpark is a way to interface with Spark. Spark is a way to do sort of data manipulation on big data sets. So every package has its own answer. Let me put it that way. OpenCL is another way to program GPUs. If you don't have an NVIDIA GPU, you pretty much have to use that. So fine, if you want to try GPUs from Python, you'd use PyOpenCL, but you wouldn't. I mean, it will be similar to PyCUDA. PySpark, if you have large data sets, fantastic, use it. But it's more of a. There too. Spark is one of those cases where you express what you want to compute. In that sense, it's similar to Dask, and then it goes off and tries to do it in the best possible way. So it's kind of having a restricted set of possible actions that it can then optimize. And in that sense, it's actually not that different from NumExpert, which also you give it an expression and it goes, I see how I can optimize this. I can parallelize that. But the Spark is more aimed at data. And that's good. Anything else that you think we should answer now, or shall we? Yes. No. Sure. Yeah. Yes. Okay. All right. I'm gonna stop here, and if there's more questions on the Slack, I'll try and answer those. But thank you.
Thank you very much, Ramses.